Good morning, dear students. In the last lecture, we were trying to understand uh, nuclear magnetic resonance spectroscopy. I hope you have all understood yesterday's lecture. Is there anybody who has not really understood the concepts? We started with the magnetic properties of molecules, the nuclei, that is, the nuclei have a spin. Of course, if these nuclei have odd atomic number or odd atomic mass number, or both atomic number as well as the mass number. If it is odd, then these nuclei have a magnetic moment. Okay, they spin around the axis. They have half integral spins. Okay, and when these nuclei have such a property, if they are put in a magnetic field, then they align themselves in the magnetic field. Okay, and then if we put if we put radio waves incident upon such nuclei, then these nuclei, depending upon their own properties, they will absorb that radiation, radio waves. Okay, and because of that absorption, they will undergo a flip or a transition in their spin. Okay, so if it is in one direction, say if it is in a parallel direction to the magnetic field, then they go to the anti-parallel direction. Okay, so that kind of flipping of the nuclei will take place. Okay, and what we do is we measure which radiation or which wavelength, that is the frequency. In terms of the frequency, we measure it. Okay, which frequency is absorbed by the nuclei to undergo the flipping transition. Is that right? And then I told you that two types of NMR are very prevalent. One is called as the proton NMR or H plus NMR, and the other is called as the carbon NMR. Okay, then I told you that this hydrogen, the proton is very predominant in nature. More than 99.9% of all the hydrogen that are present in any sample in nature, they are of the proton type. Okay, normal isotope H1. Okay, and then if we compare that with carbon 13, then less than something like 1% or so of all the carbon present in nature is of that isotopic form, that is 13 carbon. Of course, I told you that 12 carbon is not active because the net spin is 0, and therefore it does not absorb the radio waves, and therefore there is no question of any transition of the spin. Okay, so we don't use carbon 12, but we use carbon 13 for NMR spectroscopy. Okay, and then I think I told you about what did I tell you? What kind of analysis we do by NMR, which atom is present, where the atom is located in the molecule, how many of such atoms, that is the protons or the 13 carbon, how many of them are present, where they are exactly present, who are the neighbors of that carbon. And based on that information, we are trying to find out what is the structure of a particular molecule. Okay, then I told you about the instrument. We have a magnetic field, huge magnetic field is there, in which we keep the sample, and then the sample is spinning inside the magnetic field because the magnetic moment should be uniform, isn't it? And then I told you that there is a radio frequency transmitter which transmits the radio waves on the sample. And then depending upon the type of the sample, the nature of the sample, that radiation will be absorbed for undergoing the spin transition. Okay, and then we have a detector which senses how much of the radiation is not absorbed. That is, the transmitted radiation is detected by the antenna. Okay, so again, this design is very much similar to whatever we have already seen in the case of infrared spectroscopy or Raman spectroscopy or UV visible absorption of spectrophotometry. Okay, in principle, the things remain the same. Okay, but the difference here is in the type of the analysis that we are carrying out, the type of incident radiation that we use. okay, the type of detectors we are using, and all of that depends in turn upon the type of sample analysis that we want to carry out. Okay. So today we are going to see a little more detail about how the compounds are identified using NMR. Okay. So one thing I told you is about the chemical shift. Okay. So if it is an isolated nucleus, for example, an isolated proton, if we keep it in the magnetic field, then it will absorb some radiation, some wavelength, okay, depending upon what energy it is required for the flipping of the nucleus. Okay. But if that proton is not isolated proton, if it is in some kind of a molecule, okay, it may be a water molecule, or it may be any, say, ethanol molecule, or any other, say, benzene, for example, or glucose, okay, then the chemical environment of the proton is different, and therefore that proton, or in fact there are different types of protons in different molecules. Okay, I'm coming to that point a little later. Okay, so these protons, because they are in a different chemical environment, they are going to require a different energy. In fact, they will require higher energy because of the masking effect. Okay, they will require higher energy, and that kind of shift in the energy or shift in the frequency which is required for their transition is called as the chemical shift. Okay, and based upon how much is the chemical shift, we can sometimes try to find out what is the kind of the molecule, or what type of molecule it is in the sample. Okay, so let us go to little more details of that. We have a standard compound, for example, tetramethylsilane. Let me magnify my slide. I'll go to the slideshow mode. Okay, hope you can read what is written here. Okay, tetramethylsilane I have put here in bold letters. Can you see my slide? Can you all see my slide?
Yes, sir.
Okay.
Yes, sir.
So this is a standard compound, and in this particular compound we have the protons. Okay, all protons are similar here, and therefore we get a very strong peak. Okay, very strong peak corresponding to the protons which are present in this molecule CH3,4Si. Okay, that is tetramethylsilane. Okay, all the protons here of the here are of the same type. When I say same type, it means that their bonding to the carbon atom, okay, is similar. All the types of bonds which are present for the protons, they are all the same type, and therefore we get a very strong intensity peak in the NMR. Okay. Then the chemical shift actually is, see, if we take tetramethylsilane and we get a particular peak, that is called as a reference peak. Okay. Now this reference peak is given an arbitrary value of 0. Okay, because it is a standard compound we are using. Okay, and then if we put a sample and the peak changes the position, okay, that is a different wavelength is used for the flipping transition in the nuclei. Okay, that shift in the spectrum, or shift in the peak position, is called as a chemical shift. Okay, now this value for the chemical shift is a very cumbersome number. It is a very like we have seen in the case of pH. Okay, the numbers were very small. Even in centrifugation, we have seen the Swedberg unit. Okay, the numbers are very, very small. Sedimentation coefficient we have seen. Okay, and therefore these numbers are, we try to make these numbers a little more meaningful or little more manageable. Okay, so when we raise it to the power of 6, whatever number that is, chemical shift raised to the power of 6, that makes that converts it into what is called as a ppm value. Okay, and then these numbers are little more manageable. Okay, so this is a chemical shift. I have given the formula here. That is the sample frequency minus reference frequency. What is frequency? What is the meaning of frequency? Wavelength inverse. Okay, number of waves passing in 1 second. That is the frequency. Okay, so what is the sample frequency? The radiation which is absorbed by the sample. Okay, minus the reference frequency, that is for the TMS compound. Okay, tetramethylsilane. Okay, divided by again the reference frequency multiplied by 10 raised to 6. So instead of putting percentage values, we are taking the values for 10 raised to power 6. Okay, that number is multiplied by 10 raised to minus 6, so that the number becomes little more manageable to us. Okay. So these are all the values, ppm values for different compounds, CH3X, CH2X2, and so on.
सर स्लाइड दिसत नाहीये सर.
Okay, I'll share it again. Yes, now we can see that.
Yes, sir.
Okay, so these values, just look at these numbers: 3.0, 2.7, 5.3, 5.0, 3.9. Okay, so these numbers are more simple to understand. Okay, that is why we convert them into ppm values. Okay, that is 10 raised to the power 6. Is that okay?
Yes, sir.
Now for different compounds, okay, they have given the ppm values in that image. Okay, so of course we are not going to learn all those values. We don't require that actually. If you can remember one or two examples, it is just fine. Okay, that is okay. Then we come to another point, that is the spin-spin coupling, or the splitting effect. Okay, let us try to understand this. These nuclei that we have, for example, if we have a compound, okay, like water, for example, or glucose, then it has the hydrogens in it, isn't it? That is we have the protons. Okay, now these protons, there is a certain condition where these nuclei can interact with each other. Okay, because there are charges. Okay, these nuclei can interact with each other, and therefore, instead of getting one single sharp peak, normally what happens is, for complex molecules, these peaks get split up. Okay, this splitting of is also called as spin-spin coupling. That is, two different nuclei are there which are close to each other in a particular molecule, and because of the interaction of the charges, whatever band we are expecting to get in the NMR spectrum, that band or that peak actually gets split up. Okay, this is called so they split up into multiplets. What this is called as multiplets. Okay. Now, as a general rule, you can just remember that if there are n adjacent similar nuclei, okay, when I say similar nuclei, okay, it means that all the protons, for example, are bonded to other atoms in the molecule in a similar way. Okay, so if there are n number of similar nuclei, then usually we get the peak which is split up into n+1 component. Okay, let me show you in an image here. Okay, that will be more easy for you to understand. Now I have two different compounds here. Can you see that? There are two images I have shown here. One is for 1,2-dichloromethane. Okay, 1,2-dichloromethane, and the other is 1,1-dichloromethane. Okay, that is in this particular molecule, the two chlorine atoms are there on two different carbon atoms. Can you see that in the molecular formula here?
Yes, sir.
Two chlorine atoms are on two different carbons, whereas in the second image, okay, second structure, two chlorine atoms are there on the single carbon. Okay, so the first structure is 1,2-dichloroethane, and the second one is 1,1-dichloroethane. Okay, so these are two different compounds. And if you are trying to carry out NMR spectroscopy to find out the structure or to identify which molecule is which, okay, then if you can see the spectrum here, in the case of 1,2-dichloroethane, where there are 4 different hydrogens here, okay, and all the 4 hydrogens are exactly the same. They are bonded to carbon. Okay, the carbons are bonded to the chlorine atoms. Okay, and therefore if you look at the structure, you will easily be able to understand that all the 4 hydrogens are looking very similar to each other. Is that clear? And therefore in the spectrum, NMR spectrum, we get a single intense peak. Can you see this peak at 3.73? 3.73 is the chemical shift. Now this chemical shift is of course computed from the peak for TMS, that is the standard compound. The green color line here indicates the peak for TMS. Okay, TMS also shows a single sharp peak because all the protons present in TMS are of the similar kind. Is that clear? And in the case of 1,2-dichloroethane also, we get a single peak. Single peak indicates that whatever number of protons are there, they are all exactly the same. Is that clear? And the chemical shift is something which tells you about what could be the molecule. Okay, so 3.73, if that is the chemical shift, then that would probably help us to identify that this molecule is 1,2-dichloroethane, because this chemical shift 3.73 is characteristic for 1,2-dichloroethane. Is that clear? Now look at this other structure. Okay, in the other structure, that is 1,1-dichloroethane, you will find that there are two different types of hydrogen hydrogens atoms. Okay, one type of hydrogens are all bonded to the carbon, that is 1, 2 and 3 hydrogens, which are shown in red color. Okay, they are all similar. Can you see that they are all similar?
Yes, sir.
And one hydrogen which is shown in orange color or yellow color, that is bonded to the carbon, which is itself bonded to chlorine atoms. So this is a different hydrogen. Okay, so in 1,1-dichloroethane, there are two types of hydrogen molecules. Two types of hydrogen atoms. Is that clear? One is shown
Yes,
in
sir.
red color, the other is shown in yellow color. Okay, so two different types of hydrogen. And therefore, you should know that two distinct peaks we are going to get other than TMS. Okay, just ignore TMS here, but you are going to get one red colored peak here at chemical shift 2.06. Okay, and you are going to get another peak at 5.89. Okay, 5.89 ppm. Okay, and that peak stands for the other type of hydrogen. बरोबर आहे का? हे दोन पीक तुम्हाला कळाले? Because the number of the types of hydrogens are 2. Okay. आता आपल्याला काय बघायचंय की द म्युच्युअल स्प्लिटिंग जे मी म्हणत होतो, ओके, स्पिन कपलिंग. The first thing that we have seen is the chemical shift, 2.06 ppm and 5.89 ppm. There are two different chemical shifts indicating that two different types of hydrogens are there. Okay. Are you all there? Can you all hear me?
Yes, sir.
Okay. आता आपल्याला दोन्ही पीक मध्ये जर परत केअरफुली तुम्ही बघितलं तर तुमच्या लक्षात येईल की पीक नंबर 1 हियर at 2.06 is itself split up into 2. ओके, 2 मध्ये स्प्लिट झालेला आहे. आणि दुसरा जो पीक आहे 5.89 तो 4 मध्ये पीक स्प्लिट झालेला आहे. ऍक्च्युली हे कलर स्कीम जी त्यांनी दिलेली आहे ना, थोडासा मिस्टेक आहे त्याच्यामध्ये. देयर इज अ स्मॉल एरर इन द कलर combination that they have shown here. Okay, this red color peak, actually red color stands for this hydrogen, the yellow colored hydrogen. Okay, now as I told you that
Okay,
that general rule which I told you, that if there is one particular type of proton, okay, then you get two splitting lines. Okay, दोन लाईन दिसणार तुम्हाला. So here 1 and 2, these are two different lines corresponding to this proton, yellow colored proton. Okay, n plus 1. So n is equal to 1 here. Therefore, you get two different lines here, very close to each other. That is called splitting. Okay. Right. And in the other case, we have 3 hydrogens which are of the similar type. Okay. And therefore, n plus 1 is equal to 4. So you should get 4 different small lines here in the second peak. Can you see that? 4 lines.
Yes, sir.
Okay. म्हणजे 4 लाईन दिसल्या ह्याचा अर्थ तुम्हाला काय कळणार आहे की 3 protons are there which are of the similar type. and 2 lines here indicate that there is one proton which is of another type. Okay, so 2 peaks, peak number 1 red color, peak number 2 yellow color, indicates that there are 2 different types of protons, and within each type, okay, there are 3 protons of one type and there is 1 proton of the other type. Okay, so there are total of 4 protons. Okay, 3 protons of one type, 1 proton of another type. So total 4 protons are there in that molecule. Okay, and the chemical shift information is also there. So all this information together, if we analyze, okay, now there are expert people who know how to identify the molecule, how to draw the structure of a molecule based upon this kind of information. Okay, याच्यापेक्षा जास्त डिटेल मध्ये मी पण तुम्हाला सांगू शकत नाही, कारण ओनली द एक्सपर्ट पीपल हु आर लाईक डेली कॅरिंग आउट सच अनालिसिस. काही लोक हे काम डेली करत असतात, वेगळे कंपाऊंड त्यांच्याकडे येतात, न्यू कंपाऊंड त्यांच्याकडे येतात, and they are trying to find out the structure. Okay, and this structural elucidation part actually is not based upon just one instrumental analysis. ते FTIR पण करतात, ते NMR पण करतात, ते ESR पण करतात. ओके, UV विजिबल स्पेक्ट्रोस्कोपी पण करतात. असे वेगवेगळ्या प्रकारचे टेक्निक्स एकत्र वापरून एका सॅम्पल वरती they try to find out what is the structure of a molecule. Is that clear to everybody?
Yes, sir.
मुलांना ओके. काही जर डिफिकल्टी असेल तर विचार. तुम्हाला हे सगळं सिंपल वर्ड्स मध्ये तुमचा लिहिता आलं पाहिजे नोट्स मध्ये. ओके, so if you find any difficulty you can ask me anytime, you can ask me, that is not a problem. पण हे समजून घ्यायला पाहिजे तुम्ही. ओके, तुम्हाला 2 ते 2.5 पानाचं इन्फॉर्मेशन लिहिता आलं पाहिजे एक्झाम मध्ये. तुमची एक्झाम जरी ऑब्जेक्टिव्ह टाईपची असली, इवन इफ इट इज अ मल्टिपल टाइप ऑफ एक्झाम, मल्टिपल चॉईस टाइप एक्झाम, क्वेश्चन्स विल बी देअर. ओके, पण तुमच्या समजण्यासाठी तुम्हाला ब्रीफ डिस्क्रिप्शन हे लिहिता आलं पाहिजे. इज दॅट ओके? इथे पण एक एक्झाम्पल, इथे पण एक तुम्हाला एक्झाम्पल दाखवले मी, की समजा हे बघा 4 प्रकारचे मॉलिक्युल्स दाखवले मी. ओके, in one the first type there is just one proton. ओके, आणि त्या प्रोटॉनला दुसरा काही कपल्ड प्रोटॉन नाहीये, फक्त एकच प्रोटॉन आहे. ओके, तुम्हाला सिंगलेट लाईन मिळते. ओके, इथे जर 2 प्रोटॉन असतील तर तुम्हाला 2 मेजर पीक मिळतील. ओके, इथे पण 2 प्रकार आहेत इथे, बरोबर, 2 वेगळ्या टाईपचे आहेत, त्यामुळे तुम्हाला 2 पीक तर मिळतील. पण इथे जे आहे 1 आणि 1 हे 2 एकामध्येच 2 आहेत. एकामध्ये 2 असल्यामुळे ह्या 2चे तुम्हाला 3 पीक मिळतील. ओके, इथे कपल्ड प्रोटॉन एकच आहे रेड कलरचा, म्हणून तुम्हाला 2 पीक मिळाले वरती. इथे एक पण कपलिंग नाहीये, नो कपलिंग, सो ओनली अ सिंगल शार्प पीक. ओके, म्हणजे 2 प्रोटॉनचं कपलिंग जर असेल एका मॉलिक्युल मध्ये, ओके, सो फॉर दिस 1 प्रोटॉन देर इज 1 कपल्ड हायड्रोजन. ओके, 1 कपल्ड हायड्रोजन आहे म्हणून त्याला 2 लाईन्स येणार. ओके, 2 कपल्ड प्रोटॉन्स असतील तर त्याला 3 लाईन्स मिळणार, आणि 3 कपल्ड प्रोटॉन जर असतील तर त्याला 4 लाईन आपल्याला मिळणार. सो n+1. ओके, जस्ट रिमेंबर दिस, n+1. ओके, इथे पण इथेनॉलचं एक्झाम्पल दिलेलं आहे. हाऊ मेनी टाइप्स ऑफ प्रोटॉन्स आर देअर? 1, 2 and 3 टाइप्स ऑफ प्रोटॉन्स आर देअर. रेड कलर, ग्रीन कलर आणि ब्लू कलर मध्ये दाखवलेले. कॅन यू सी दॅट? Because there are 3 types of protons, you get 3 different peaks. 1, 2 and 3 peaks are there. प्रत्येक पीकला काहीतरी कपलिंग कॉन्स्टंट आहे, that you can find on the x-axis here. आणि मग तुम्ही बघाल की एक प्रोटॉन आहे इथे, तर त्याच्यामध्ये 2 लाईन दिसणार तुम्हाला. ओके, 1, 2, 3 प्रोटॉन्स आहेत तिथे तुम्हाला 4 लाईन दिसणार, आणि 1, 2 प्रोटॉन आहेत तिथे तुम्हाला 3 लाईन दिसणार. ओके, अशा प्रकारचा पॅटर्न तुम्हाला दिसतो, आणि दिस पॅटर्न हेल्प्स यू टू फाइंड आउट व्हॉट इज द स्ट्रक्चर ऑफ अ पर्टिक्युलर मॉलिक्यूल. ओके, देन कमिंग टू द लास्ट पार्ट, दॅट इज द ऍप्लिकेशन्स ऑफ NMR. पण पुन्हा मी तुम्हाला सांगतोय की इथे मी जे ऍप्लिकेशन लिहिलेले हे खूप थोडक्यामध्ये, अगदी एक एक छोटस लाईन मी इथे लिहिलेलं आहे. ओके, पण जेव्हा तुम्ही तुमच्या नोट्स तयार कराल तेव्हा यू हॅव टू राईट अ लिटिल मोर डिटेल अबाउट द ऍप्लिकेशन. ओके, स्ट्रक्चर ऑफ मेम्ब्रेन, स्ट्रक्चर ऑफ बायोमॉलिक्यूल, स्ट्रक्चर ऑफ काय म्हणता येईल वेगळे वेगळे ड्रग्स इथे दिलेलं नाही मी. ओके, ड्रग मॉलिक्यूल एस्पेशली दिस इज व्हेरी युजफुल फॉर अंडरस्टँडिंग द स्ट्रक्चर ऑफ ड्रग्स. एक मिनिट मी पुन्हा शेअर करतोय. ओके, लेट मी राईट इट डाऊन हिअर. Structure of bioactive molecules, structure of drugs, okay, especially the newly discovered is that clear to everybody? Newly discovered bioactive molecules or drug compounds, याचं स्ट्रक्चर फाइंड आउट करावं लागतं. मोठ्या मोठ्या ज्या कंपनीज हे सगळं काम करत असतात त्यांना. ओके, सो फॉर दॅट पर्टिक्युलर ऍप्लिकेशन NMR इज अ व्हेरी व्हेरी युजफुल डिव्हाइस. ओके, टू फाइंड आउट द स्ट्रक्चर ऑफ मॉलिक्युल्स. अजून काही तुम्हाला सुचेल का याच्यावरती ऍप्लिकेशन? तुम्हाला हे थोडंसं इलॅबोरेट करता येईल. ओके, इव्हन आपण हे पण लिहू शकतो, स्ट्रक्चर ऑफ मायक्रोबियल यू कॅन से सेकंडरी मेटाबोलाइट्स. इज दॅट क्लिअर? सेकंडरी मेटाबोलाइट कंपाऊंड असतात, मायक्रोबियल असेल किंवा इव्हन प्लांट्सचं पण असेल. ते प्लांट मधनं काही वेगळे वेगळे कंपाऊंड्स आयडेंटिफाय केले जातात. इवन एस्पेशली आयुर्वेदिक प्रिपरेशन जे करतात लोक है ना, बेस्ड ऑन सम मॉलिक्युल्स ऑब्टेन फ्रॉम प्लांट्स, तर त्याचं पण ते स्ट्रक्चरल आयडेंटिफिकेशन करू शकतो आपण. इज दॅट क्लिअर?
Yes, sir.
एनी क्वेश्चन अबाउट NMR? इथे पण मी काहीतरी अजून एक स्लाइड बनवली आहे, पण ही थोडी कॉम्प्लिकेटेड वाटेल तुम्हाला, सो डोंट रिफर टू दॅट स्लाइड. ओके, दिस वन इज ओके. फक्त ह्याच्यात थोडं थोडं इलॅबोरेट करावं लागेल तुम्हाला. ट्राय टू पुट लिटिल मोर डिस्क्रिप्शन. ओके, सो दॅट युअर ओन अंडरस्टँडिंग अबाउट द टॉपिक विल बी गुड. ओके, अँड देन यू कॅन अटेम्प्ट मल्टिपल चॉईस क्वेश्चन्स बेस्ड ऑन दॅट प्रिपरेशन. इज दॅट ओके? त्यामुळे आज मला तुम्हाला एवढंच सांगायचं होतं NMR बद्दल. In the next part we will see mass spectroscopy. Okay, एकच राहिले ना आपलं आता. If you have a copy of syllabus you can just refer to that. Okay, latest copy of the syllabus. आणि त्याच्यात काही राहत असेल तर ते मला सांगा. Then I can cover all those points. एक मला वाटतं ॲटॉमिक फोर्स मायक्रोस्कोपी राहणार आहे याच्यामध्ये, तर ते मी तुमचं नंतर घेणार आहे. ओके, ॲटॉमिक फोर्स मायक्रोस्कोपी थोडं नंतर घेईन मी. Is that okay? So maybe by tomorrow आपल्याला एक लेक्चर पेपर 1 चा आहे ना. सॅटर्डेला काही लेक्चर नाहीये. तर आपण काय करू, उद्या पेपर 1 आहे रिसर्च मेथोडॉलॉजी, आणि सॅटर्डेला मला लेक्चर नाहीये. तर इफ आय गेट 1 एक्स्ट्रा लेक्चर, जर काही मॅनेज करता आलं तर सॅटर्डेला मी एखादे लेक्चर घेईल. अदरवाइज ऑन मंडे अँड ट्यूसडे आय ट्राय टू कव्हर दिस कम्प्लीट युनिट. ओके, स्पेक्ट्रोस्कोपी. ओके, अँड देन आय विल स्टार्ट विथ अनदर युनिट, थर्ड युनिट. इन द मीन व्हाईल तुम्ही सगळं प्रिपरेशन तुमचं चालू ठेवा, नोट्स वगैरे रायटिंग चालू ठेवा, आणि युनिट नंबर 2 ची टेस्ट मी परत घेणार आहे. ओके, युनिट नंबर 2 ची टेस्ट कधी घेऊ मी, तुम्ही सांगाल का मला? नेक्स्ट लेक्चर मध्ये सांगितलं तरी चालेल मला, किंवा तुम्ही व्हॉट्सअप वरती जर सगळ्यांनी मिळून जर डिस्कशन केलं तरी चालेल. यू कॅन ऑल डिस्कस ऑन युअर ओन ग्रुप and then you can let me know on the official group which date you want the second internal test. Is that okay?
Okay, sir. Yes, sir.
Yeah.
Yes, sir.
काही क्वेश्चन्स आहे का तुम्हाला या टॉपिक बद्दल, NMR बद्दल? FTIR इन रामन बद्दल काही क्वेश्चन्स आहे का? फ्लुरोसन स्पेक्ट्रोस्कोपी, नेफेलोमेट्री, टर्बिडिमेट्री, UV विजिबल स्पेक्ट्रोफोटोमेट्री, याच्याबद्दल काही प्रश्न आहेत का? काही असतील प्रश्न तर मला तुम्ही विचारू शकता. आत्ता विचारा, नंतर विचारा, काही प्रॉब्लेम नाही. एनी टाइम यू कॅन आस्क मी. प्रिफरेबली हे सगळ्या मुलांच्या देखत विचारलं तर चांगले, कारण सगळ्यांना ते कळेल, सगळ्यांना प्रश्न पण कळतील, क्वेरी कळतील आणि त्याचं उत्तर पण कळेल. ओके, सो प्रिफरेबली वी विल डिस्कस अबाउट एनी क्वेरीज ऑन द क्लास. ओके, क्लास ग्रुप वरतीच आपण करू. Okay, shall I stop the lecture then?
Okay, sir.
Okay,
Yes, sir.
so bye everybody.
Thank you, sir.
Okay,
Thank you, sir.
thank you.
Thank you, sir. Bye.
Yes, bye.